It all starts with an observation, a simple experiment. You take a laser and shine it onto a specially crafted half-silvered mirror, also called beam splitter, designed to reflect exactly 50% of the incoming light and let through the other half. You also place a detector in each path. For now, both of them detect half the light from your laser. Something interesting happens, however, when you start decreasing the laser's intensity. At first, nothing surprising happens, as each detector still measures half the light. But at some extremely low intensity, instead of the previous splitting, you find that sometimes all the light shows up on one detector and sometimes all on the other. The energy sent out is no longer divided, but rather randomly going one or the other way. You've just discovered that light comes in tiny, indivisible units, called photons. This finding that light is quantized is also how Albert Einstein earned his Nobel Prize. Because it cannot be split, when this single unit of light hits the half mirror, it is either reflected or transmitted, each with a 50% probability. Over many iterations, these events even out, and on average you again receive the same energy at each detector. So the high power case can be recovered by averaging over a bunch of single photons. But it's still a bit strange, isn't it? After all the photons are the same, so how are some reflected while others are transmitted? Determined to find out, you head back to the lab to take a closer look. You might already know that light can also be described as a wave in the electromagnetic field, something you'd notice if you zoom in on the micrometer scale. In this picture, your laser produces a moving wave at a fixed frequency, whose amplitude corresponds to the light's intensity we've been adjusting. And for a single beam, this is really all you need to think about. But once there are two or more beams, there's also the question of how these light waves are shifted relative to each other, something we call phase. Two beams can be in phase, meaning all their peaks and troughs align, or out of phase, for example by quarter of an oscillation. If they're shifted by half a wavelength, then their peaks are exactly opposite. One can say they're completely out of phase. As you can see, once they're shifted by a full oscillation cycle, they become in phase again. This symmetry is reminiscent of going around a circle, which is why phase differences are often measured in multiples of pi. So once you have multiple beams, in addition to some amplitude A, you also need a second value to keep track of their relative phase, telling you how these waves are shifted compared to each other. Conveniently, these two pieces of information can be combined into a single quantity, using complex numbers which also feature the circular symmetry. A phase shift of pi over 2, for example, then corresponds to multiplication with the imaginary unit I, and a phase shift of pi, meaning half an oscillation, to a factor of -1. Now, -1 times amplitude may sound odd at first, but if you remember that phase is a relative relationship between two waves, it actually makes a lot of sense, because when these two beams overlap, every maximum of one lines up with a minimum of the other, causing the electric fields to cancel each other out. This concept is important because your half mirror splits the incoming light into two beams, and you need to check their phase relation to fully understand your experiment. So you grab some sort of phase meter, go back to the lab, and discover that the reflected wave is shifted by half an oscillation compared to the transmitted one, meaning they are completely out of phase. Now I should mention that this measurement depends a bit on what kind of beam splitter you bought. There are essentially two common designs, the asymmetric half-silvered mirror and the symmetric beam splitter cube. In the asymmetric design we're assuming here, light reflected from one side gets a half oscillation pi phase shift corresponding to a factor of -1, while reflections from the other side have no shifts at all. Whereas in the symmetric design, reflections on both sides get a quarter oscillation shift, corresponding to a phase of pi over 2 or a factor of I respectively. What's important, however, is that every half-mirror design introduces some phase shift somewhere, and everything we'll explore today will be valid no matter what design you choose. In fact, a beam splitter with no phase shifts at all would violate conservation of energy, but that's a story for another day. In this video, we'll simply assume you bought the asymmetric option to avoid juggling with imaginary numbers, but it really doesn't matter. Returning to your experiment, let's write down what you've observed. Firstly, the half mirror normally splits the incoming intensity into two equally strong beams. Secondly, for light coming from the left, these beams are shifted by half a wavelength relative to each other. And finally, when repeating the experiment with single photons, each photon randomly ends up in one of the detectors with equal probability. With this list of observations, you decide to employ some mathematics to get a new perspective on what's going on. To do this, you introduce a vector that keeps track of which path your light is currently in. For your setup, we'll distinguish between a horizontal and a vertical path. Initially, all the light is in the horizontal path, which we denote with a 1, 0. After the mirror, only half the light continues horizontally, while the other half is reflected onto a vertical path. To respect that the total amount of light didn't change, the vectors before and after the mirror must have the same length or magnitude, calculated as shown here. In this case, they both have a length of 1. You satisfy this condition by choosing 1/2 for both x and y of your output vector. We further account for the phase shift in the reflection by adding a minus sign to that component. This vector thus tells us that there are equally strong light waves in both directions that are completely out of phase. And while we came up with this formalism to describe the splitting of intensities in the case of many photons, we can use the same notation to describe the single photon experiment simply by swapping our interpretation of the numbers from relative intensity to probability. So for the single photons, we read the same vector as saying there's a 50-50 chance for the photon to end up at either detector. Next, we want to model the behavior of your half mirror. It will be the operator h that transforms the first vector into the second vector, and it should reflect the correct phase relation, respecting that for the asymmetric design, there's only a phase shift for light coming in from the left. This often takes some trial and error, but after some thoughtful tinkering, you may discover that this matrix here gets the job done. You now have a compact mathematical description of your experiment, generally a big step forward in physics because it allows you to play around with ideas in the abstract without rebuilding your lab every time. In this case, if you mess around with the matrix for long enough, you might notice that applying it twice in a row again gives you a state where all the light ends up on one path. Back in the lab, you test this by using two mirrors to steer the reflected and transmitted beams onto a second half mirror, and sure enough, they recombine into a single beam, just as if there were no half mirrors at all. We can also explain this observation physically by looking at the phase relation of the two light waves. The reflected wave from the first half mirror comes in horizontally into the second half mirror and is completely out of phase with the wave coming in from the top. However, upon being reflected again, it picks up another half oscillation phase shift, putting them back in phase. Meanwhile, the transmitted part gets no new phase shift and thus cancels out with the other beam. So the math checks out, but does it also hold if we again reduce the intensity to the single photon regime? Remember, with the single photon and a half mirror, you always saw just one detector click. It seemed like the photon simply picked a path at random, like having a rotating laser that randomly sends the photon sometimes this way, sometimes that way. But if you think about it, right before this photon hits the second half mirror, the situation looks exactly like our first experiment. Based on this, one should expect the photon to end up at some detector at random. This is indeed what happens if you take the rotating laser from our analogy. We get the 50-50 distribution. But when you actually use the two beam splitters, you always find the photon at the bottom detector. So the assumption that the photon is essentially flipping a coin to pick a path must be wrong. Yet we also found out that the photon cannot be split and arrives as a compact particle. So how does it do that? In the high intensity case, the behavior was explained by interference. That's fine because two waves can interfere. But how can the same outcome be found for a single particle where the concept of phase doesn't even make sense because there's no other thing to reference it to? Well, what does the math say? Remember, for the first experiment, we always used the same equation and merely changed our interpretation of the numbers from intensities to probabilities of where the photon ends up. In this case, the same approach would correctly predict a probability of 1 for the photon to end up in the lower path. But what does changing intensity to probability mean physically? If in the high-power picture the numbers denote intensities of propagating light waves that can interfere with each other, then does the single photon probability picture mean that there are abstract waves of probability flowing through space, capable of recombining and having phase relations? That's certainly not how probability works in everyday life, where it usually describes our state of knowledge. When rolling dice or predicting the weather, there's obviously nothing going through space to interfere before the results appear. So from a perspective of physical intuition, this sounds like complete nonsense, and the math stays silent on the details. It predicts the correct result, but it doesn't tell us why. Very unsatisfied with your findings and determined to finally figure out what's going on, you now place a detector into the top path to catch the photon in the act. It is a clever plan. If the detector clicks, you know the photon must be in that path, and if it doesn't, it can only be in the other one. So you run the experiment. Half the time, the new detector clicks, exactly what you'd expect if the photon randomly takes a path. But what happens if it doesn't? In 2025, quantum mechanics turns 100 years old, and in this last century, the observation you're now going to make has caused a great deal of headaches to physicists all around the globe. Because even though detector 1 stays silent, receiving 0% of light and energy, its mere presence changes the outcome of the experiment, as the photon no longer always ends up at detector 2, but now randomly again at either detector 2 or 3. The fact that you're now observing one of the ports changes the outcome regardless of whether you find something there or not. This is a massively disruptive observation. Nowhere in classical physics has there ever been an interaction, a change of outcomes with zero transfer of something like energy or entropy. So how can we explain this unsettling dynamic? Well, you're not going to like it, but we can just start by extrapolating the math from the classical scenario again. In the case of a lot of light, blocking one path means half the light is dumped before reaching the second half mirror. With only one incoming beam there, no interference can happen, so the beam just splits again. In the end, 50% of the light goes to detector 1 and the other 50% is divided equally between detectors 2 and 3. With this, we have no problem since the energy is just distributed among the 3 detectors. If we now switch intensity for probability, again leading us to this cursed idea that the photon's evolution is modeled by this non-tangible wave of probability, then by squaring the amplitudes, we determine the detection probability as 50% at detector 1 and 25% at detectors 2 and 3. We again find the correct result, and we again have no idea what kind of wave it describes. And while this is beyond the scope of this video, we can even prove by using something called quantum entanglement that if there is something that our detector is just unable to detect, that something has to violate special relativity. The weirdest thing is that from a mathematical point of view, the crucial ingredient for interference seems to be a lack of information. There has to be a non-zero value in both entries of our probability vector. The moment we measure one path, whether we find a photon there or not, one of these entries becomes 0 and interference is impossible. Note that up to this point, this interfering wave of probability is just a mathematical construct extrapolated from classical wave dynamics. It works astonishingly well in predicting this and many other experiments, but that doesn't mean that this probability wave physically exists. From a philosophical side, it's all very blurry, but a common understanding of contemporary quantum theory tells us that before a measurement, a photon isn't a tiny unit at a specific place, but rather it's a delocalized entity capable of taking all available paths simultaneously. Many physicists believe a measurement then collapses this spread out state into a single localized particle. Yet we don't know why this collapse happens or even whether collapse is the right story. All we know is this: while it appears as a single blob on our detector when measured, before a measurement, the evolution of a photon and any other quantum particle is best described by a wave-like spread of possibilities. Different possibilities can then mathematically interfere and enhance or weaken each other. A necessary condition for this interference is that there are at least 2 open possibilities, so once you know where the particle is, it cannot interfere anymore. In your experiment, the detector, whether it receives the photon or not, shows you the path the photon is in. Physicists say the detector reveals the which path information, thus changing our vector state and preventing interference. If you're confused at this point, that's good, you should be. For 300,000 years, we humans have developed a fantastic intuition for the physics happening on our scale, and only in the last century, thanks to huge developments in technology, have we discovered that classical mechanics is just a special tame corner of all the physics happening in our universe. And for everything outside this corner, we develop no intuition. Still, you might think there's surely a better explanation for all of this, and while this is impossible to rule out, you should know that this has only been one experiment and there are 100 more weird quantum effects that can all be perfectly predicted using this framework. In fact, in the last century, quantum mechanics has emerged as perhaps the most accurate and successful scientific theory ever devised. And amazingly, despite its contextual weirdness, the math behind this is very simple. In fact, that's one of the coolest things about quantum mechanics. You see, in classical physics, there are many systems which are governed by highly complex equations, even though every child has an intuitive understanding of the physics. In quantum mechanics, it's the other way around. No one understands what's going on, but the math is essentially just linear algebra. To give you a better feeling for the strangeness of these quantum states and also to tackle the question that all physicists are afraid of, what is this all good for, I want to show you one last experiment. And trust me, it's a good one. For this, imagine you're handed 10 closed boxes. Unfortunately, half of them contain a hypersensitive bomb that will explode if even a single unit of energy touches it. You can check what's in a box by shining light through it. If the box is empty, the light passes through, but if it contains a bomb, you trigger an explosion. Your job is to find the bombs while causing as little damage as possible. Classically, there's no way around it. You have to interact with the box to check what's inside, giving you a 50% probability of detonating a bomb. But now put the box into the upper part of your interferometer, where the extra detector used to be. Then the following happens. If the box is empty, the photon can pass freely, and the two possible evolutions recombine at the second half mirror so that the photon always ends up at detector 2. However, if there is a bomb, half the time the photon will go there and set it off, but the other half of the time it ends up in the lower path, never touching the bomb. However, since the top path is closed now, there is no second possible evolution to interfere with, so the photon randomly ends up at detector 2 or 3. Note that whenever the photon ends up in detector 3, it means there is a bomb in the box, despite never coming into contact with the photon. All things considered, there's a 12.5% probability for this to happen, and hence for you to know that there's a bomb without detonating it. A probability that's strictly zero classically. And by the way, this is not hypothetical. People have conducted versions of this experiment. Also, while these 12% might not sound like a huge improvement, you can actually chain together many of these setups to make the chance of setting off the bomb arbitrarily small, allowing you to eventually identify all bombs without detonating a single one. This principle of cascaded interference also underlies Grover's algorithm, one of the earliest developments in quantum computing, able to perform an unstructured search faster than all known classical alternatives. This is not the time to explore this connection, but I'll put some resources in the description. To wrap up, quantum mechanics follows simple mathematical principles that describe a behavior no one yet understands, and that allows us to do things that our classical intuition says are impossible. Some of them might even be useful.